Okay, so I'll formally start the proceedings. So it's actually a pleasure to get all of you back after the whole week. So I'll formally start the proceedings. So it's actually a pleasure to get all of you back after the whole week. So I'll formally start the proceedings. So it's actually a pleasure to get all of you back after the whole week. So I'll formally start the proceedings. So it's actually a pleasure to get all of you back after the whole week. So we start. It's actually a pleasure to get all of you back after the so we start. It's actually a pleasure to get all of you back. Wait. So, well, I don't know why this is the case. That I can't pull out. Well, I don't know why this is the case. That I can't pull out. No. What has happened is the YouTube is on there and it has its own volume that is switched on. So it has gone into loop. This is why I can't see. This is a resolution problem on the desktop. This is why this is a resolution problem on the desktop. Oh. यहाँ पे चाहिए ये वाला हाँ इसको वो बंद कर दिया हाँ बंद कर दिया okay start again. Okay, we are back up. As you heard multiple times, I was welcoming you all after the Holy Week. So, it's always good that we have a physical colloquium. Since 2020, there have been times where we had online colloquium, but for this one, we have our speaker, Professor Hugo Dill, here. Before we actually go and formally introduce my colleague, Professor Shouvik Chatterjee, is going to introduce Hugo. I would like to state to all of you hearing on YouTube, as well as those who are joining us for the first time, that the colloquium series is pretty old. It actually was started by our founding director, Professor Homi Bhabha, and it allowed for Professor Bhabha to meet all the faculty on one of these days, that is the Wednesday of the week, and also together with all the faculty would listen to one of the visiting experts visiting the institute at those dates and listen to a colloquium. So this has been a tradition. It has benefited both the faculty members internally because it has actually enabled physicists, chemists, and biologists to be in the same platform and discuss things that are being discussed, talked about in the colloquium. So it has been a very, very fun series for us. And it's a pleasure to host you, Hugo, here. Now I move on to Shouvik, who is going to formally introduce you.
Thanks, Jyotishman. So it's a great pleasure to have Professor Hugo Dill visit TIFR. And so I'll just give a short introduction of him. So Hugo is a professor of physics at EPFL, and he's also a scientist at the Paul Scherrer Institute, working at the Swiss Light Source. So his experimental research interest focuses on how reduced dimensionality and symmetry influences the spin properties of materials. And I guess we'll hear a lot about that in this talk. Hugo received his PhD from Fritz Haber Institute and Freie University in Berlin, Germany. In 2014, he was awarded the Heinrich Rohrer Rising Medal by the Surface Science Society of Japan for his leading and creative roles in identifying novel spin structures using synchrotron radiation-based both spin and angle resolved photoemission spectroscopy. He was also awarded in 2015 the University Latsis Prize for his work on topological insulators and for the identification of spin interference. So without much ado, I'll welcome Hugo again for his talk. Looking forward.
Okay. So thank you very much for the introduction, and thank you also for being here and allowing me to be part of this long tradition. I did not know that it's probably one of the few colloquium series in the world which has been going on that long. So it's an honor. Yes, So actually, I will not be talking too much about reduced dimensionality. I thought for a bit this more general audience, I talk a little bit more about general physics, and I wanted to revisit a little bit of quantum mechanics, actually, and especially focus on two examples of it that you might not be thinking about that much. Which is actually what happens if we make coherent superposition of spin states. And the other thing that I will get to, and it's where I will be using this coherent superposition of spin states, is actually talking about what is the time scale of quantum mechanical processes. And so really the role of time in quantum mechanics. And I actually prepared a little bit to introduce myself, but it's already been done. So I'm originally from the Netherlands, and from Amersfoort. I studied philosophy after my high school in the US. And it's also will be towards the end of the talk, will be more about that. But then I realized, okay, to move on in life, it's better to study physics. So I started. Actually, I always wanted to study physics, but I did not. After high school, I was a bit bored with it for a moment. I wanted to do something else. So I studied physics in Delft at the Technical University. Then I went to the Fritz Haber Institute in Berlin. And that's where I started using synchrotron radiation. And then I started my postdoc at the University of Zurich. And then since 2013, I'm at the EPFL. So just to indicate, so there's actually not many people on Zoom, right? So I prefer to use the laser pointer. So the EPFL is part of the no, I switched it off.
Oh, again, switch it on.
Okay.
Right.
Yes.
Yes.
Yeah. So the EPFL is part of the so-called ETH domain. There are many institutions in there, and most of them are in the German-speaking part of Switzerland, and we are here in the French-speaking part on the Lake of Geneva. So this is the EPFL campus. My office is somewhere there. Actually, from our campus, we have a view on the Mont Blanc, which also, of course, plays a tragic role in the history of this institute. So, but it's still a beautiful mountain. It's and there we have the synchrotron, neutron spallation source, free electron laser. This is actually the big storage of nuclear waste of Switzerland. And these are my two affiliations. So let's get going about quantum mechanics. And so, I mean, you've heard a lot about it, and let's just see what we can learn from popular fiction about quantum mechanics. And we go back to before actually quantum mechanics was invented. And Lewis Carroll, he had already with his Cheshire cat. It's actually we know it's in a superposition of being there and being gone. But what I like as well is this statement from Alice in Wonderland, which is for me actually a little bit like the single particle double slit experiment. So if you have an electron, you have two slits. It actually interferes with itself going from one place to the other. So if that was already the status before actually the Heisenberg description of quantum mechanics, afterwards it must have become much better, and we can only look at popular science and then know everything about quantum mechanics. Unfortunately, it's actually only went downhill from there. If we now look at the latest versions of quantum mechanics in popular science, it's this quantum mania. There we have in the quantum world things that are flying around. We have people or living in quantum world. No. So I'm really sorry. I cannot do it with popular science alone. I have to go to real physics to explain it. And I thought, okay, the best way to do that is to introduce a bit my group. because then we have all the ingredients in it. So the name of my group, I called it spin-orbit interaction spectroscopy. And the main reason was just I like the name in French, soi. It's be. It's the imperative of être. And we can generalize research in three parts. Okay, one is like the focus on spin orbitronics. And I will talk a bit more about it in the seminar also tomorrow about these things. It will now only come back slightly. We look at novel physical phases, especially topological phases and everything, and how this influences the spin structure and the properties of materials. But what I will talk about a bit more today is like we use it as an extra tag. In spectroscopy, we consider the spin-orbit interaction. And an example where I would not be talking about, for example, one can study on conventional superconductors and then see the role of spin-orbit coupling in it and everything. So let's break down the name a little bit. So first start with the orbitals. I don't know if there are many chemists here, but then they feel at ease. The orbitals, of course, it's just a probability distribution of electron around the core. And if you start hybridizing orbitals, or you start mixing orbitals to hybridize, you can easily mix them together. And in solids, that's in principle what you do. And you just get a superposition of the different orbitals that you're around. And the symmetry then still remains. An example of it, if you start with infinitely separated orbitals, you bring them closer together, they start to overlap, and they actually start to show a band structure together. And these kind of things is what we're looking at. Okay, so that's the orbital part. The basis is already quantum, and there's not much quantum going on. So let's consider now the spin part. You are probably aware that it was introduced by Uhlenbeck and Goudsmit to explain the double lines observed in atomic spectroscopy, and it was then introduced pretty much as an intrinsic angular momentum, and this is also how it is introduced in most basic physics lectures. It's just an intrinsic property of the electron. You should not think about it. And here I want to just highlight that there is a different explanation of it. One explanation that you often hear in popular science is just like it's the spinning of the electron around itself. That's completely wrong, of course. That we all know. But there's this nice paper from Belinfante, who's also in Leiden, just like Goudsmit, but just a decade later. And he actually already explained that the spin can be considered as the circulating flow of the energy in the wave field of the electron. So it's not the circulation of the energy of the electron itself, but the energy of it. So it's not just some magic description, but you can go for it. For me, what's important about spin is just we have to consider spin as a vector pointing somewhere in three-dimensional space. We can describe it on the Bloch sphere. And what I will using and what's important, that's why we'll spend a little bit of time on it, is that we have to describe it based on the basic vectors. And I chose it here, the basis vectors in the basis of Z, but one can rotate them around, but that's not important. And important is now to see, okay, how they're constructed. They're complex vectors. And for example, the interesting thing is if you sum plus Z and minus Z together, you get X. And this is the same idea as for angular momentum. You cannot destroy angular momentum. And this will be an important point that I will get to, these kind of summations to explain the spin interference. Okay, next part is we have the spin, we have the interaction. And it's a busy slide. There's a lot of things going on. For me, the important message is, okay, once we have spin-orbit interaction, and you have that always. For in a crystal, you have it always, even if you have hydrogen. You cannot anymore talk about only the spin or the orbital components of your wave function of your entity. So you have to talk about both of them. You get a mixture. Another way of looking at it, you always have to associate one spinner, which can be just pointing anywhere in space, with one orbital. And then if you combine this with symmetry breaking, with magnetism, with very generic other characters, then a whole realm of physics opens up, and that's a little bit where I've been navigating over the last 15 years to look at what's going on. The important point here is if we consider magnetism. This is probably what you're more used to if you're talking about spin. You have a real space spin order. So the spin is defined on the atom, on the electron, and it's in real space where you know where you are. And the dynamics is slow. It might be nanoseconds, but nanoseconds is slow for me. Whereas if we talk about spin-orbit interaction, what we get is actually a spin order in reciprocal space. So in Fourier space in that sense. And that's what we'll be focusing on. And the dynamics is much faster. It's on the order of femtoseconds or even below. So then the last part, the spectroscopy. So what I do primarily is photoemission spectroscopy, which of course goes back to the idea of Einstein, of the quantization of photons, or the idea of photons, and that the kinetic energy of the electron leaving it is the photon energy minus some price that you have to pay.
Could we just go back one slide? And just expand on this idea of how you're explaining the spin orbit interaction in the order of femtoseconds. Could you just explain that?
Just why the dynamics, why it's femtoseconds or why it's fast?
Femtoseconds.
Okay. Just it's based on the energy scales associated with it in that sense. I would,
okay, it's just the energy scale that you're converting.
Yes.
Okay.
So
the order of energy for the spin orbit
yes.
coupling, that's all what you're translating. Okay. And the other thing is the reciprocal space spin order. Could you just expand that as well?
I will expand on it in a little bit.
Perfect. Yes. Thanks.
So there's no people from the Max Planck actually came here, right? It's because maybe they might not be happy with this next. Well, it's actually about Max Planck. So when he was nominating Einstein for the Prussian Academy of Science, he actually wrote that, okay, he was saying, okay, Einstein is very good, but I mean, he missed the point with his idea of photons. That was, but no, don't worry about it. I mean, we all make mistakes. With his last statement, I agree again, and it's also for any young scientist. You cannot really advance without really being willing to sometimes make mistakes. The important thing is then you should admit your mistakes afterwards if you realize it, which I'm not sure if Max Planck did. That's not in history. Okay. So how does this work? Angles of photoemission. So it's a photon in, electron out technique. If we measure the kinetic energy of the electron from energy conservation, we get the binding energy of the electron in the solid. We measure the emission angle. Then from momentum conservation, we can get the momentum of the electron in the solid. And if you combine this now together, so here lighter colors are higher measured intensity, you can make these kind of pictures, which is the band structure of the solid. So this is like a calculated band structure for copper. This is the measured one, and these are the SP bands. These are the D bands, and typically you just get a nice overlap or a nice comparison. or you can sit at one energy and then you get what you would call a Fermi surface. The idea behind it is if it is technique, these kind of maps, in principle, you can show how the electrons are moving in the crystal. This is a very simplified way, but the important thing is you can get all the properties of the electron, how they are behaving in the crystal.
In this kind of map, how do you construct the 3D Fermi surface?
The 3D Fermi surface, this is a little bit more complicated. So you would actually have to repeat these maps for different photon energies. So with the change of photon energy, you change actually the out of plane momentum. The problem with this is due to the potential step at the surface, the out of plane momentum is not conserved. So there is an offset, and this is typically empirically you have to find it. But you can then make a full 3D Fermi surface. I do not have anything here now. I can look at some examples of it after the talk to show you. But then you get a full 3D Fermi surface.
They tune the energies of the photons.
You change the energy of the photons, yes. And while always looking at the Fermi energies,
Sure.
also you change the energy where you measure the electrons, of course, at the same time.
The fact that you will get the penetration depth of the photon.
The penetration depth of the photon doesn't matter at all, because that's of the order of micrometers. So what is relevant, and I did not talk about it here because I could give a 2-hour lecture on angular photon emission alone, is actually the escape depth of the electron. This is very small. This is of the order of a couple of angstrom. And if you increase the energy, then you increase this escape depth. But it's a very, very slow increase. And then there are other things. So to measure this 3D Fermi surface, it's better actually if you go to higher photon energies where your escape depth is larger, because in real space, it's larger. In reciprocal space, it's better defined. So your KZ is better defined. But these are things. Okay, so the thing which is in our specialty is to also measure the spin. And for this, we have the coffee machine at the Swiss Light Source. And here, coffee stands for the complete photon emission experiment. And why do we call it complete? Because it's besides the energy and the momentum, it also measures the spin. And it measures the spin in really as a vector or expectation value or in 3D space. And how does it do that? So instead of measuring the electrons after they've been energy and momentum filtered, we accelerate them again towards so-called Mott detectors, which is just a gold foil and then some 4 diodes, which is count electrons. And if you now have an electron coming with this spin, it has a higher probability to be scattered like this. If it has the opposite spin, it has a higher probability to be scattered like that. So now I have my 2 detectors. I measure the difference in intensity between them or the asymmetry, and this gives me how much spin polarization is along this direction. Then I have my other detectors, and this way I get my my 3D space. Okay, so now yes. So again,
the z-axis of your spin. You don't have a magnetic field.
we have no magnetic. This is very. It comes back also to like what is our quantization axis? Is
Exactly.
your question?
Yeah.
Okay. So our quantization axis is actually we define it a posteriori. So we define it from our measurements, and in the sense it is defined by where we measure in reciprocal space. There is no unique. The quantization axis of the spin in our systems depends on our measurement positions, and this is the interesting thing of spin-orbit interaction.
Okay.
But I will get to that in just one minute why this is the case. So in this respect, if you have a magnet You would say, okay, ferromagnetic spins are pointing along the magnetization direction. It's very simple. We're talking about this. So this is the spin that I will measure of my states. I find magnetism either too simple if we just look at it like this, and if we think about it a little bit more, it becomes too complicated for me. I do not understand anything anymore. So we hardly look at magnetism. Tomorrow I will talk a little bit about it, but so we look at other sources, and some other sources of spin polarized initial states are Rashba systems that I will get to in the next slide, or for example topological surface state. Again, I could give a several hours lecture of our last 15 years of research into topological materials, but here I just want to show highlight two things. We can have systems or geometries with different topology, and we take the example of, for example, a normal band and a Möbius strip, and you directly see if we go from a normal band which has two surfaces and two edges, and if I go back to the same point, I need a phase of 2 pi. If I go to something with a different topology, the Möbius strip, I have only one surface actually. I have only one edge, and the phase to get back to the same point is 4 pi. So just by changing the topology, it's really you have something different. But here, what's the important thing is to go from one to the other. You cannot continuously deform one into the other. You have to go through a singularity. Or in mathematical terms, you would have to, or mathematical terms, you say you have to go through a singularity. Physical terms, you would have to close and reopen the gap. And this is already, then we go back to this paper from Shockley from 1938. He showed that every time, as a function of some parameter, you close and reopen the gap, you have some surface states that appear. So this we know already since almost 100 years, and it has become a hype in the last 15 to study these surface states because they have special properties. One of the special properties that they have is actually their spin polarization, because to make sure that they exist, this kind of topological protection, this being a singularity, they have to be spin polarized. And then you get these kind of Dirac cones and the spin just going around it like that. I'll show some more examples of this later. Just one thing I want to highlight for anybody who wants to start in this technique, be careful that all photoelectrons are highly spin polarized. If you see a spin polarization, does not mean anything that your initial states are spin polarized. But that's just a side remark that I will get back to. So Rashba type spin orbit interaction, this is a more typical source of actually spin textures in reciprocal space. And then it also comes back to this idea of what is your quantization axis. Consider a potential step, which you naturally have at the moment that you have a broken inversion symmetry or a surface or an interface. And now you have an electron traveling in the plane perpendicular to this potential step. So in the rest frame of the electron, the electric field associated with this potential difference is transformed into a magnetic field, just by Lorentz transformation. So, and a electron in a magnetic field experiences Zeeman splitting. So the energy levels are split according to its spin. So then you have the electron going to the right. You would have its spin. Actually, it would be its spin pointing like this. Would have a different energy than the electron with the spin in the opposite direction. If it has zero momentum, then there's no splitting because the Lorentz transformation gives zero. And if it changes in the opposite direction, then this splitting will be opposite, or the spin will be different. And of course,
can I ask a question?
Different.
Sorry, yes? Can I ask a question? Sorry, I stopped you in the explanation. You talked about the electric field. The structure of the electric field matters in this case, how it is structured, if it's helical, if it is chiral, for example, in some sense.
The electric field.
Yeah, you talked about in the so as the electron.
In this explanation, the electric field is just purely a uniform out of
Just a directed
the
pointed electric
explanation. The second half of the slide is it goes into the Coulomb field, which is
Okay.
the better explanation.
Okay, sorry. So you said that as far as I understood it, that in through the Lorentz force, which was
Lorentz transformation.
Lorentz transformation.
So not the Lorentz force.
Okay.
It's
Could you
not the
explain?
Lorentz force.
Yes,
It's the
okay.
Lorentz transformation of the electric field in the rest frame of the electron.
Okay, it's a
Relativistic,
relativistic
it's
effect.
yeah, it's just your
Okay. So it's a Lorentz transformation to sort of have a rest frame for the electron at that speed. Is that?
yes. So you
Okay.
do the Lorentz transformation with the reference frame of the speed of the electron.
Okay.
So you move along with the electron.
And in
then
that
you
frame,
have the
you have the
then
Zeeman
that's
splitting
you get the electric field is transformed into a magnetic field.
field, and you get the Zeeman splitting.
And then you just have an electron
Okay.
in a magnetic field and you get the Zeeman splitting.
Okay. And under that constraint, you are now switching the energies of the two polarized electrons, right?
Yes, because
Okay.
I'm switching the momentum.
Okay.
So if it's going to the right or to the left, of course, the sign in my Lorentz transformation changes.
Sure.
It's a plus
Right.
V or
Okay.
minus V.
Okay.
So it's the sign of the magnetic field changes as well.
Okay. Okay.
So this is then you have in sense that you have a momentum dependent quantization axis. This is exactly where it then comes because you have a momentum dependent magnetic field or pseudo magnetic field.
Okay. Thank you.
Okay. So the problem, and if you look at different directions, so you always get this going. It's in the first approximation isotropic. So you get these two concentric circles as Fermi surfaces, which are with spin winding clockwise and counterclockwise. And if you look at it in 3D, it's actually two intersecting paraboloids. Problem with this model is it's 6 orders of magnitude wrong, but the symmetry is correct. And the mistake made is that the electric field that's relevant is not the macroscopic electric field of the interface, but it's actually the electric field of the Coulomb potential, which is relevant. And then it's no longer, then if you have a Coulomb potential, of course you have your electron, it's at both sides, so there's no symmetry breaking anymore. So now something has to break the symmetry, and this is actually then the macroscopic electric field, which does that, which just slightly shifts the wave function. And then you get the Rashba effect. But this is just a side remark. And then you can directly also understand that it's very strongly dependent on atomic corrugation and displacements, because this means that the electron wave function it can no longer follow in a simple picture the position of the course. Okay. So we were talking about spin, and let's continue a little bit with spin and play with it in reciprocal space. And we have some symmetry considerations. One of them is time reversal symmetry. So again, I'm talking about mostly about non-magnetic systems. So time reversal symmetry is obtained, which means that if we have changed the direction of the momentum, we change the direction of the spin. This is also what you saw in the previous slide. Positive momentum, we have one spin, negative momentum, the other. Okay. But I don't know how many of you are thinking about this actively, but that a spin is also a pseudo vector. And what does it mean? This is every angular momentum is a pseudo vector. But so what does it mean? That if we do a mirror operation on the spin, we actually have to flip its sign. So this gives us constraints in our crystals what spin textures one can have. And for example, if you would take an out of plane spin pointing along the z direction, this is only permitted for alt-rotational symmetry. Because if you would take this C4 symmetry, if you have out of plane here, then time reversal symmetry would say it's pointing in the opposite direction here. Crystal symmetry would then say, okay, here it has to be pointing out of plane again. Then crystal symmetry from here to here would say it's pointing in the inside, but we started with pointing outside. So we get a contradiction. So this means an out of plane spin is not possible for symmetric axis. Okay, now let's go to spin interference and look at it a little bit more. So we take our basic vectors of spins of our spinors. So again, I said, okay, we start with just arbitrary with z, calling it 1, 0 and 0, 1. Of course, if we sum it together with a phase 0, we get the 1, 1. If we sum it together with a phase shift of pi, we get 1 minus 1. So that means depending on the phase with which we sum it together, we get actually a spin pointing. So we start with two spins like this, we sum them together, you get, depending on the phase, you get a spin pointing in this direction. If you have a phase shift of pi, you get it pointing in this direction. If you have a quarter pi, you get 1i, so you have to point it along the y direction. And if you have 3/2 pi, you get it pointing in the opposite direction. And of course, everything in between. So to illustrate this, here I have two spinors, actually not taking them opposite, but actually taking them almost parallel. It's just, and it's interesting to illustrate this. And here, this is just as a function of the phase with which we sum them. And then you see actually that if you sum them with a given phase, you can actually get a spin which is almost opposite. And the easiest example is just you have two spins, which is here, I change one spinor, and then I sum them with a fixed phase. And if they're opposite, then I have a spin in the plane perpendicular. But this is the whole idea of spin interference. So that if you have different spinors, you sum them together, you get a spin in a different direction, depending on the phase and the prefactors. Let's now see if we can measure this in any systems. Actually, it was the other way around. We measured it, did not understand it, and then we realized this is how research works, right? It's the fun part. So why did I talk about the Rashba system? Because here, this is a Rashba system with a very small splitting. We cannot resolve it, but in here, there are actually two bands. Later on, people have resolved it with very high resolution. They see these two bands, but they're very, very close together. With our spin resolved measurements, if we now measure here, we put a cut here. This is our intensity that we measure. It's just like these three peaks and a little shoulder here. And then we get the X, Y, and Z components of our spin polarization vector. It's just a way of displaying it to get a 3D vector to display its components. So the blue line is what you just expect, okay, for a Rashba system. It's the Y direction is here perpendicular to the momentum. This is your spin polarization that you would expect. And it's actually on the position where is the peak maximum. It actually has a zero crossing. But you see the most significant signal that you see is actually this red line. It's along the X direction. And it has its maximum on actually where the peak has its maximum. So this is actually here, the blue and red is back calculated from this, from the Y polarization. So if we now would assume this is initial state spin polarization, then we actually say, okay, we have positive momentum, we have spin up, we have negative momentum, we have spin up. So we've broken time reversal symmetry. So in that sense, I would have to tell you that antimony on silver would have to become magnetic. You would send me away laughing and chase me probably into the ocean, and you would be justified to do so. So what's actually is happening is that here, these two opposite spin polarizations, they create this summation of actually having a spin polarization in the plane perpendicular. So let me illustrate that a little bit more. So we start with our lines and we assume there are no interactions in the first step, just sharp lines. Then we apply some experimental broadening, and then we would just get our this kind of rushbar only on the y direction, what we would expect, this up-down behavior. But if there are some interactions which conserve the phase, which is, for example, the scattering with defects, you actually already, your initial states, they become quasi-particles. They become already broadened. And now if the splitting is so small that they actually overlap, then from this region, the electrons do not know, in a quantum mechanical sense, whether they come from one spin state or the other spin state. So at the end, they're in a superposition of both spin states. So the measured states in intensity would still look the same, but the measured polarization would be showing this in this plane perpendicular to it.
And can I just ask, so this is antimony single layer of atoms on top of
it's a third of the monolayer, third of monolayer of antimony on silver. And it's so every third silver atom is replaced by antimony.
So if you change the silver to some other metal, will this effect be smaller or larger? Can you tune this effect?
Yes, to tune it, I will get to. If you change the silver, it also works on copper and gold.
Okay.
That's the easiest because you need the same crystal structure. Of course, the others have, but there are also many other systems where similar effects work on. You can also do it on silicon.
Okay.
But to change it, it's actually easier to say, okay, I replace some of the antimony with bismuth, which is heavier. So the spin-orbit coupling is larger, but also it's larger, and so it buckles more outside. So it increases the spin splitting. So what we see is actually that with increasing bismuth content, these two peaks that were overlapping, they're moving further apart. So as a result, then the out-of-plane spin polarization that we measure is being reduced. So this is really, this was the first show of spin interference happening experimentally, seeing it in photoemission. At that moment, the community was not ready for it, and it was said, okay, this does not exist. If I have two quantum states with opposite quantization, they cannot interfere, period. Whereas if you just take your Pauli matrices, it's directly obvious.
What was the broadening in the second row?
The broadening in the second row is just for example, lifetime broadening, experimental broadening, the resolution of our setup, those kind of things.
Oh,
this broadening or this broadening?
No, that broadening, yeah.
This one.
Yeah.
This broadening is due to, I mean, you have this kind of crystal structure.
Yeah.
So there's actually there are impurities. It's impurity scattering.
I see.
And so maybe there's the antimony is slightly there, or it's already, you have silver and antimony, there's already scattering happening.
Crystals, this effect would be reduced.
If a perfect crystal, this effect would be reduced. I do not have the data. We saw the same thing actually for the copper surface state. And if we prepare the crystal, if I prepare the crystal, then we see it. If my students prepare the crystal and they spend a lot of time and making it really nice and perfect, then this effect is reduced.
I see.
So it's and that gives the idea it's really like a kind of defect scattering, because a energy loss kind of scattering, this would be incoherent, and then your phase would have changed, and then your coherent overlap would be ill-defined.
But can you controllably increase defects and see this effect increasing or decreasing?
In principle, one could, yes. But it's to of course calibrate the amount of defects. It's we just have it just by how good you prepare the sample.
I see. And the sample itself, is it a crystal or
It's a single crystal
A
of,
single
of
crystal.
silver, which is atomically clean, and then in UHV, this third of a monolayer of antimony is deposited on it.
I see, and then you keep stacking, or it is just a
It's one
bilayer?
interface.
One interface. So then what is this picture that you are showing?
This is the top view, and this is side view.
Oh, I see. Oh,
Sorry, it's a little bit smaller than it's probably hard to read from the back. Okay, so maybe I will just go very quickly through this because I want to get to the time because I do not have much time, right?
No, it's okay. You're doing fine. You still have 15 minutes.
Okay, but I still will go. So I want to show that before we had, I showed it, okay, we have these Rashba states. So we have two states we bring closer together. But the effect is more fundamental. We can even have it if we now have two orbital compositions or two orbitals which make up the same state. One orbital has one spin associated with it. The other orbital has another spin associated with it. And for this, I use the example of the Dirac cones in topological insulators, which have been studied. We were the first to measure the spin story, but afterwards have been studied a lot. And one of the things that was surprising us always from the beginning, we always measure a spin polarization of 100%, whereas theory says it should be of the order of 60%. And I will get to it why this is in the end. So again, because of spin-orbit coupling, spin is no longer a good quantum number. And as a result, depending on which orbital you probe, you actually get a different spin polarization. So this is an example, the same sample measured with p-polarized light, which probes the pz orbitals, and s-polarized light, which probes the py orbitals. So I'm now talking really about the orbital symmetries like in one of the first slides I showed. And the spin polarization just changes sign. It's down, up, and it goes to up, down. This is with a laser-based ARPA setup. This has been shown more clearly. And again, it's always 100%.
When you are looking at the orbital here, are you looking at the atomic orbital? Which orbital is it?
Sorry, I did not understand.
when you talk about the orbital, which orbital are you talking about? Is it the atomic orbital that you are talking about?
Okay, which orbital is it? So I'm talking about the atomic orbitals that make up the bands that we're interested in. So
Okay.
so we have our atoms. We bring them together in a crystal. The orbitals overlap. They make up a Bloch state, which has then some orbital symmetry. And so the orbital symmetry of this band is actually a mixture of all the three p orbitals.
I see.
With a little bit of s, but we can forget about that for the moment. So it's the three p orbitals, px, py, pz,
Okay.
which make up this state.
I see.
And now with the light polarization, we can probe which orbitals we probe primarily.
So Px and Py are symmetric.
In this case, yes. And pz is
Is the one that is
yes.
different. Okay.
So now if we measure the spin polarization along it, we keep our light polarization fixed, but we change the photon energy. Then we see, and we look at all three the components. So not only at these components, which are the ones going around the circle, but we also look at the components perpendicular to it. We see that these components perpendicular to it are significant, especially here, the Z polarization can be pretty large, and that they change with photon energy. So again, what is the explanation for this? This is that actually these spinors, that is the clockwise that I probe with one light polarization, the counterclockwise that I probe with the other light polarization, that they actually sum up. So they are within the same band. So I do not need any broadening or anything like that. They overlap, they interfere with each other and give a spin polarization in the plane perpendicular to it. And now where this points, this depends on the phase. And my phase with which they interfere, this depends on my photon energy because it changes the selection rules in my photoemission process. This goes a little bit fast, but just believe me in that. So I have the same picture as I had before, but instead of two circles that I bring close together and interfere, I have it within the single state. This has also been very beautifully measured by the group of Shixin in Tokyo, where they actually, we can change the photon energy. They, with their laser setup, they cannot change the photon energy but they can continuously change the light polarization without changing the photon intensity. And this experiment that they did, so this is comparable to what I showed you before. You just have one light polarization and the other, and you see that the spin polarization is switched. But again, what's happening, what's interesting is what happens in between. So these are the three spin polarization components. So the blue one is just the one which is clockwise or counterclockwise. And the green and red ones are the ones in the plane perpendicular to it. So you see that where blue goes to zero, blue, green and red are maximum. So actually the spin has completely rotated in the plane perpendicular to where it should be, according to theory. And this is due to the interference of both of them. And there the phase of interference is actually such that it's, or actually the prefactors here, that it adds up. Okay. So what are some of the general consequences of this? First of all, this spin interference, it was known already, especially in India, by Datta and Das, and they used this actually to propose their spin transistor. That actually the idea is you come in with a spin in, like we say here, in the plane perpendicular to the slides. You decompose it in these two spins. Then they have a different momentum. So when they travel through the crystal, they acquire phase difference. Then after some distance, you sum them together again because you reach your next interface. And then actually the spin has rotated, and then either it can go into the drain or it cannot, and those kind of things. It doesn't work as good as they hoped, but it's the physics is correct. So it does not work because the phase loss is problematic. You really need to have a narrow channel where you define it to, because otherwise you start averaging over different momentum values, and there they have different phases and everything. And then after this distance, you actually get for this momentum value slightly away from. So for this one and this one, you might actually get an opposite spin, and it cancels out. So the nice thing of the spin interference is actually, in principle, and this is what we showed in photometry, you can, if you can change the phase, you can get a photon beam with a control, or an electron beam with a very well controlled spin polarization. This applies to any interface. If you can control the phase at some, for example, some tunneling interface or something like that, you can control the spin of the electron, but you have to be able to control the phase with which they appear. Typically, we cannot, especially in transport, this is very, very difficult. And the spin interference is actually the reason why you lose your coherence, your spin coherence, when something travels through a system with larger spin orbit coupling. This is known to everybody, but it's just nice to see the mechanism from a quantum mechanical point of view. Tomorrow, if you would have states with a pure spin, so no different orbital composition, but all the orbital components have the same spin, then this effect would not be the case. And tomorrow I will give an example of that. But now I want to actually show, okay, that we can use this concept to measure something completely different. And this now brings me to time. And so it's a completely different topic now. So for those of you who have fallen asleep, in case you can wake up again. So just it's the question, what is time? And I've looked it up, of course. What is the Hindu concept of time? It's primarily described as being cyclical. For the rest, there's no fundamental idea of time. It's just more the time on the large scale. Or I did not find it. I'm happy to discuss anything else. So we have time. Aristotle is one of the first who really explicitly started writing in it, and I'm of course very Western biased. So that's and he said, okay, time is just something that describes before and after, puts order to things. It's also he really was the first to start thinking about it. Okay, the future does not exist yet. The past does not exist anymore. The now clearly does not exist because it has no dimension. So time does not exist. And it started confusing. St. Augustine made his famous remark, okay, what's time? If nobody asks me, I know, but if I have to explain it to somebody, I have no idea anymore. But let's go a bit more to physics. These are two interesting things. We have been, primarily in physics, we use Newtonian time. And then we use the Einsteinian correction to Newtonian time. But it's still this idea of there's a kind of universal time. That time is something which is beyond physics in a sense. For Newton, it was really a fixed block given by God pretty much. And Einstein then showed, okay, time is relative. But even with that, we do not get far. Leibniz, at the same time as Newton, actually said, okay, already said that time is something relative. So if we would have listened to Leibniz already at that time, probably general relativity would have come about a couple of centuries earlier, and we would have been much further. For him, time was always something more flowing. So yeah, to come back, I visited in Jaipur the observatory where they were very proud to be able to measure time with a resolution of 2 seconds, which I must say for that construction, it's very impressive. But what I'll be talking about is attoseconds. So that's a little bit more. So what do we know about time in quantum mechanics? And if you ask somebody, they would probably say, okay, we know how time is in the Heisenberg uncertainty relation. It's the uncertainty relationship like between position and momentum is the uncertainty relationship between energy and time. Unfortunately, this is not a uncertainty relation. This is just a Fourier transform. This has nothing, we learn nothing about time here. It just tells us that one observable with respect to energy can only be observed with a certain precision. So no time in there. If we want to learn something about time, it does nothing. So let's see what Pauli said about it. Pauli wrote, okay, time is not a quantum observable, it's just a classical parameter. So he treats it pretty much like Newton. But then later on, he started doubting. And it's also because actually one has to separate, just like we do for space, we separate between distance and space. We also have to separate between time duration and time as a universal thing. And then it can be a quantum observable. With, again, some problems. Its operators are not self-adjoint. And then you have the issues of defining time zero. So the function of time in quantum mechanics is still not clear, and it becomes even worse if we want to now start linking it to more relativistic ideas or the quantum mechanical idea of entanglement. Everything breaks down in a sense. We will have to start talking about instantaneous, and So what I want to focus on is actually what would be the kind of times in a quantum mechanical sense of the time for the wave function to decohere. And doing photoemission, one would say, okay, one does time resolved photoemission, ultra short pulses. We do this as well, but again, it does not give any information about time itself. It gives you impose actually the time system by the frequency or the repetition rate of your laser. And so you say this is the time coordinates, and that's what you get. You can do beautiful experiments with it. This is a very nice example, but then there are people trying to go into the attosecond scales. It's sense that, okay, you have to go to attoseconds if you want to see quantization effects of time. It's just like you do not have to go to the Planck length to see quantization in space. You do not have to go to Planck time scale to get quantization effects in time, or quantum effects in time. Let's put it like that. And just to speed up a little bit, because the chairman is sitting. So here the problem is with all these kind of techniques is that you only get the time delay of the quantum transition, that's photoemission, with respect to some reference. You do not get really the intrinsic time. So what we did, and this is the PhD project of Mauro, who's now in Paris, rapidly rising through the ranks. And here's actually the Mont Blanc. And also inspired by Ulrich Heinzmann from Bielefeld, is we started to look at it a different way. Can we, without imposing any time, but get some information about time? And through that, the key is in the spin and the phase that I just talked to you about. So for this, we look at photoemission as a half scattering process. So the photoemission process, you go from initial state to final state. You can describe your matrix elements by real part and imaginary part. And in this imaginary part, we have the phase. If we now compare this to the so-called Eisenberg but Wigner-Schmidt picture, which is a picture to determine, okay, what is the time that a wave spends somewhere in an interacting potential. You actually look at it at the phase shift as a function of energy, and then the derivative of phase with energy is time. And this is then the time that you have of the interaction, of the process that's taking place. So in photoemission, we do not have, of course, a wave coming in and coming out. We create it in that moment, so we have to look at it as half scattering. So again, going very quickly to the end, we just have to remove this factor 2. It's a little bit more complex, but that's what it comes down to. To get the time scale of the photoemission process, we have to look at the derivative of the phase with energy. And I just showed you that there's a direct link in photoemission to these things like phase and spin. In the sense that, okay, even if I have a spin degenerate state, and this is where it goes, it's different from what I showed before, where I showed, okay, the interaction between two spin polarized states. Now I take a spin degenerate state, but with my photoemission process, I still select certain orbitals. And these pathways, if there's more than one pathway, these will interfere and will create a certain spin polarization. This is the simple picture. So we also have done experiments where there are no two pathways, but there's only one pathway, then this process, we cannot use this measurement. So, but two different, so you have two different matrix elements that describe your transition from an initial state to a final state. There's not just one pathway, it is one pathway associated with one orbital component and one with another orbital component. And because everything is degenerate, I do not say which one. I select, I have a certain probability to selecting more one than the other with my light polarization. That's why actually here the whole geometry of the experiment actually comes in. It's the geometry of the symmetry of the band structure, the symmetry of the experiment, the symmetry of the universe pretty much goes in there. And this looks very simple, but then you need a Mauro to work it out. It took him 3 years to get through the algebra. I made it small on purpose that you do not try to read it. But in the end, what matters now? So there's a direct link between spin polarization and phase. There's a direct link between derivative of phase with energy is time. And so there's a prefactor, a correction prefactor in front of it, which is dependent on this geometry. But in principle, one can say the time of the transition is equal to the derivative of the spin polarization measured as a function of energy. So now what we do, we just measure our bands, we measure the spin polarization as a function of energy, and we get the time. Let's see how that works. Start with copper, just the most simple material, nice SP band, measuring spin polarization. We do it in a random order and change it, of course, to not have any systematic effects. Take the total spin polarization as a function of binding energy, plot it, get the slope of it, apply our geometrical prefactor to it, and but even if you just in this case, actually, geometrical prefactor is 1. So now you get the time delay of this photoemission process is 26 attoseconds. So this is the time the photoemission process takes. This is not the time that it takes for the electron to leave the sample. It's not the travel time. It's the time to go from the initial state to the final state. Later on, it will be the question, what do we mean with final state? Final state is not, of course, the electron in the detector. That takes much, much longer. In 26 attoseconds, the electron hardly travels any distance. Attoseconds are very short. Just for anybody who did not read, there's many attoseconds in a second as there are seconds in the age of the universe. Just to give you a feeling for it. We can separate this in different parts. Which is the total time delay and the scattering part of the time delay. And this is the part which is really directly similar to the Eisenberg-Wittner-Schmidt picture that I showed before.
The structure seen in that function of energy.
Yes.
But is just a derivative is one number that you are using there.
Yes.
But the structure seen in that corresponds to what?
This structure?
Yes.
Oh. I would say this corresponds to systematic errors still. I mean, this is exactly where I want to go, but we need higher resolution measurements. I want to see, for example, if we go in these areas, is this real? Is this, for example, where we get like some influence or measures some influence on the spin due to quasi-particle like electron-phonon interactions or electron-polaron those kind of things. But at this moment, we're not ready for that yet. But that's our dream. Yes.
But here, what is the origin of the polarization in copper? Is it like a very tiny spin orbit coupling? That's why.
No.
So what is the
scattering? It's pure scattering. It's scattering of the electron on. It's actually.
But there's spin dependence coming in from somewhere, right?
So if you mean you have to break the symmetry. Yes, the experiment breaks the symmetry. I have my photon coming in, my electron leaving. This is what breaks the symmetry in this scattering picture. We can discuss, but I think in the nature of time, I will skip. But it's very nicely described in this amazing book by Joachim Kessler. Not for band structures, but for atoms. What happens? So, if it works nicely for something simple like copper, the next thing you do is take one of the most complex materials that you can think of to measure. So you measure a high temperature superconductor, which was a horrible choice, actually a very difficult measurement. There the bands are much weaker. So to have time, we actually could only measure with one, and we get the slope, but we get something of the order of 85 attoseconds instead of this 26. I see the chairman is standing, so I will come back to this point later. So it seems like there's a connection between correlations and the time scale. So this is very recent data. It's my student sent it to me last week. If we now looked at charge density wave compounds, and we looked at copper telluride and titanium diselenide, we get timescales of the order of 200 attoseconds. Where we take a very similar compound, titanium ditelluride, so it's pretty much the same structure as titanium diselenide, we get 20 attoseconds. So this is an uncorrelated system. We get something similar to copper. This is strongly correlated systems. We get something similar to BISCO, or even larger. So it seems to be that there is a correlation between strength of interaction and the time scale of the process. So it seems like if there's an interaction, the electron has trouble actually making the transition. But this is all very preliminary. So now, if you allow me one moment of philosophy. So what I presented you is the idea, okay, there's a certain time delay, there's a certain time associated with it, and this causes a phase shift, which then causes the spin polarization. And this is how I presented it. But you can also say there's a certain phase associated, or phase shift associated with this quantum transition, which is responsible for the spin polarization and responsible for actually the time. And in that moment, you would start seeing time as an emergent property. So that actually time is something which is created at the moment that there are quantum transitions. And this then actually, in a sense, goes back to some of the pictures that you have from thermodynamics, that the time and increase of entropy are associated with each other. And this is, I'm happy to philosophize about that later as well. But it's a lot of things now seem to go in the direction that time is an emergent property. So let me just go to the most important slides. It's the people who've been doing all the work, and past and current members of the group. It's a very small group, and with this I leave you with my final message, that we can actually, using spin, we can access some fundamental quantum phenomena and have fun with it. This was the main thing for me. So this interference of spin state yields a spin in a new direction, which you can control by the phase. And I've shown that we can measure the intrinsic time scale of quantum transitions by spin resolved photoemission, and that these are probably influenced by interactions. And I thank you for your attention and your patience.
Thank you, Hugo. That was pretty deep talk. So I have a quick question before everybody starts. You said two things that is kind of interesting. One is that for all ARPIS measurement, that means when you look at the photoelectron emission, every time it's polarized, right? So spin polarized. So that's part of the thing that you were just discussing. So can you explain that final state and the initial state? What does that final state mean when you consider that in the last experiment, classes of experiments that you're doing? You're just looking at the polarization created per energy change. So that means you are changing, you're scanning through the energies, and you're computing something which is time.
Yes.
So could you just explain what that final state means?
So the final state in this picture, and this is just in this picture that we're talking about here. Some people, if I talk to Ulrich Heinzmann, his final state is the is the photo hole in the and the electron in the detector. But that's a different final state. What I'm talking about
That's
here,
transit time.
yes.
Right.
But what I'm talking about here is actually you have the state below the Fermi level, which is excited to a state above the Fermi level.
Yeah. Okay.
And this state above the Fermi level, this
Okay.
excited state,
Right.
this is my final state.
Right. Okay.
And then it starts to move away.
Okay. So that is 26 attoseconds.
That's 26 attoseconds.
Okay.
If you had calculated using the knife thing that you said is not correct.
The uncertainty principle between these two energy levels, applying delta E, delta T is of the order of the Planck's constant. What would you have gotten?
So to the you mean the if we take the Heisenberg uncertainty relationship
Exactly.
between the two, no. I mean, we would this was the comments that we received first. We are far breaking the Heisenberg uncertainty relationship.
Oh, that
If you would look at it like this, these time scales and the energies, they are they do not apply. But this is because we do not observe time, we observe spin, and we get time from that. So we do not have to worry about the Heisenberg uncertainty relation.
So when you say breaking this time scale is smaller or larger than what you have gotten from Heisenberg uncertainty?
It's much smaller. No. It's sorry. It's the time scale is much larger.
But much larger contradiction because Heisenberg.
No. Sorry. I'm now mixing things.
Any spectroscopy, you have a spectrum.
Yes.
You have a full width of maximum,
Yes.
right? And what you would derive from the energy band.
Yes. This is
intrinsic time scale
Yes.
of the spread.
yes.
Now that is after the detection is done.
Yes.
So it will include everything that has happened.
This is actually what you're then talking about is the lifetime of the photo hole.
Yes, the light.
This is and this is of the order of femtoseconds. So it's much larger.
Much larger than what this.
So then, wait. So then what is this time? What is the time that you, so it comes, what's the meaning of that? We can understand what's the meaning of the other one.
I will try to. I mean, it's one thing is we're still trying to exactly pin it, but we go into fundamental quantum process. Our picture is this is the time needed for the initial state wave function to decohere, and the final state wave function, so the electron in the excited state to form.
Okay, so then what is the Heisenberg one?
The Heisenberg one is just a Fourier transform.
Which would effectively the Heisenberg one is related to this, isn't it? Once you get the transition happening, how can that time be not related to the function in the
I understand.
initial state and the function in the final state?
You mean that the time is determined by the energy difference between the states?
Transition, so transition away from initial state to final state, this time will take into consideration the time that required for the initial function to completely recover and again to collapse in the state.
I think I understand what you mean, but in that sense, I think you have to look at it more like a Rabi oscillation.
Okay, I see.
It's yes.
It's the width of the transition.
Yes.
Or is it the interaction time of the light with the?
No, this is.
That is
So it's you mean the time it takes to absorb the photon?
Correct, in some sense, because that is what you are claiming is adding to your space in the spin system, right?
The time,
The final, you are not actually adding any constraint to your final state. I mean, in the ARPAs, in general, in the ARPAs, right? I mean, your degeneracies are more or less, mainly dictated by the initial state. So, I mean, what is, let's say, I mean, I have some degeneracy, right? So if I understand what you're saying correctly, if I have a complete lifting of the spin degeneracy, you will not get this spin interference. This is what you are showing, that if you could split the Rajba, right?
and if you have pure orbitals, yes,
right?
yes.
There is no interference.
But there would still be a time. But I would not be able to use this technique to measure it. Correct. Yes.
So now, so basically it is the mixing that is, I don't understand how completely, I think how the light is creating the polarized, the spin, how the spin is coming in the copper picture. But it seems to me then the time has to be related with the interaction of the light with your spin system or with your electrons. I don't know if that is something, how to think about it.
It's not, but it's also we changed the photon energy, and it's in this picture. I of course I cannot completely exclude because we're still trying to understand what is the exact details, and these are the kind of questions we're asking ourselves. But it's. Because interaction potential. Yes, but this time to absorb the photon. I mean, if you compare these time scales to the wavelength of a photon, it's extremely short. You have hardly one period of it. So it's the time that actually your picture is the time that starts after the absorption, but. This being said, you can also, of course, define that absorbing the photon means actually making your transition. So now we have but it's not just the absorption of the photon in the sense of like a semi-classical picture of absorbing. How long does it take for the photon to stop? It's the quantum mechanical picture of how long does it take to transfer the wave function of the photon and the initial state electron to the final state electron. This would be then, and then it would be the absorption of the photon in that sense. And so it's not only the wave function of the electron which has to decohere, it's also the wave function of the photon which has to decohere. And you know there's the probability of exciting an electron, it's 10 to the minus 9 or something like that with a photon. So this is the idea, but it goes into all of these things together, and I wanted to also to put it to actually to start thinking a bit different about time and about these kind of, and start posing these kind of questions.
Okay, there is a question from TP Singh. Could you unmute? It's muted right now.
Yeah, can you hear me?
Yes.
Yeah, so I have a question about the status of time in quantum theory. Let me give a short background. As you mentioned, Newton distinguishes between the absolute mathematical time and the common time, which we also call a duration. When Einstein took this to relativity, he sort of gave away, the absolute time in entirety. Whereas in reality, what he's talking of is the durations have become relative. So Lawrence and I think also the philosopher Bergson took the point of view that since durations are relative, there is no reason to give up on the absolute mathematical time. And that was Lorenz's version of relativity, equivalent to Einstein's version. In quantum theory, it would probably be very useful if we retain this Newton's absolute time. And Stuckelberg, in his fully relativistic formulation of quantum mechanics, did something like that. He raised the duration the common time also to the status of a quantum observable, and use the Newtonian absolute time as a parameter. Now, if this were to be true, one would expect to see what we could call quantum interference in time experimentally, possibly around the attosecond scales, which you have been talking about. And there's some discussion in the literature. Have you looked at this? That's my question, quantum interference in time, where you see sort of fringes in energy or in time, if you could do such an experiment. Thank you.
So if I understand the question correctly, whether we have looked at quantum interference in time or
Yes.
No, this would be one of the ideas where can we take it to this next level? Can we go so short that we see these kind of effects of what's happening on time itself? Is
it doable in the future, near future, such an experiment?
Whether it would be doable.
Or are all the measurements are essentially in some frame, it's interference of some sort of the time.
Yes, so now you would have to.
So the 26 attoseconds is not pure, or
I mean,
because you're doing a bulk measurement in any case.
Or an ensemble measurement.
Ensemble measurement.
Yes. So it would now be. I would have to think about it, how whether one could push it to something like that, and what one would have to do. I mean, one goal which going in this direction is like, okay, to for example measure these kind of timescales on entangled states, and then see whether there is like some connection happening. But this is at the moment still a thought, but that's where one would go. I think one would have to go to entangled states and look at it to see these kind of effects, because we would never be able to measure a single particle.
So that's the point. The single photon, at a single atom, and then you have to have correlated two atoms. That's what you have to do. So
yes, but from a single electron, we do not get a spin.
Of course,
there's no spin polarization.
Right. Right. Okay.
Wavelength that we are using for this photoelectron, and what is the pulse width that we are talking about?
So the photons.
The light source, basically.
The photon energy is of the order. We tried different photon, but let's say between 20 and 80 or 90 eV, or even we tried 126 eV. So in that range. And pulse duration. These are durations of hundreds of nanoseconds. So the pulse duration does not play a role. This is the difference with the other kind of experiments that I unfortunately had to go through pretty quickly, where you really use ultra short pulses. But then the problem is you define time with your pulse, and this we want to avoid. And of course, this could also be, now if you do the same kind of things then with ultra short pulses, maybe you get extra information out of it. But then you do have to worry about the Heisenberg uncertainty principle, because then your states become broadened beyond recognition.
So I will end the colloquium, because I think, to be very frank, we are very confused. And I would say in a Hindi movie, for a thing that Bruno Dil Mange More, one more talk to understand. To understand this a little bit better. So I think you're speaking again tomorrow for
yes, but then it's more
in some other audience.
I think who is giving a talk, Prentice Matter talk tomorrow at 4:30, you do 4:06. So whatever.
Right.
That will be about ferroelectrics and multiferroics.
Okay. Well, thank you very much for stirring up the conversation on time, and we have run out of it. So thank you.
Thank you.